So today we're going to talk about a mole, and in chemistry, the chemists like to joke about the mole being like the animal mole, but we'll find out today that it's not. A mole actually represents a number, a really, really, really big number. 6.02 times 10 to the 23rd. That's a 6 with 23 zeros after it. It's a huge, huge number. And the reason that it's a really big number is because it's around to count very tiny things like atoms and molecules. The word mole is like the word dozen. So if I say you have a dozen eggs, that means you have 12 of them. If I say you have a mole of eggs, that means you have 6.02 times 10 to the 23rd. So why do we use this? If you have 1 mole of any element, you have 6.02 times 10 to the 23rd atoms of it. Okay, so 1 mole of carbon means you have 6.02 times 10 to the 23rd atoms of carbon, and 1 mole of hydrogen, same thing, 6.02 times 10 to the 23rd atoms of hydrogen. 1 mole of an element also means you'll have the element's atomic mass or molar mass in grams. And we find that on our periodic table. So if you go to your periodic table, you'll see the average atomic mass at the bottom. In the example of sodium, there's 22.9. And you can find carbon has an average atomic mass of 12.01. That is to say that carbon will weigh 12.01 grams if you have 1 mole of carbon, right? So we know that oxygen atoms don't weigh 16, but if you have 1 mole of oxygen atoms, it will weigh 16. So that's why you're going to need your periodic table out for this entire thing. So we're going to use this average atomic mass as what we call our molar mass. So if you find potassium on your periodic table, it's number 19. It has an average atomic mass of 39.10. Okay, that tells me that 1 mole of potassium has 6.02 times 10 to the 23rd atoms of potassium and has a mass of 39.1 grams. So if I were holding 39 grams of potassium in my hand, I would be holding a mole of potassium. 1 mole of carbon, 6.02 times 10 to the 23rd atoms of carbon, and it weighs 12.0 or 12.01 is what's on our periodic table. And I want to point out to you that depending on the periodic table that you're using, you might see a different value of significant digits represented. So I wrote 12 here. This one has 12.011 and yours has 12.01. That's why these numbers never count towards the sig figs because they can be different depending on which periodic table you're looking at. Now we know that atoms come together to form compounds, right? So we can take carbon, and if carbon bonds to oxygen, it forms something called CO2. So if you have 1 mole of CO2, it means that you have 6.02 times 10 to the 23rd molecules of CO2. All right, now remember the CO2, if you'll remember from the last chapter, has the oxygens on the side, and there's a carbon double bonded in the middle, and that's what a CO2 molecule looks like. So again, if you have 1 mole of those, you have 6.02 times 10 to the 23rd of these. By the way, that would mean you'd have double 6.02 times 10 to the 23rd times 2 atoms of oxygen because you'll have twice as much. If you have 1 mole of any ionic compound, you have 6.02 times 10 to the 23rd, what we call formula units of it. Now, formula units is a funky word and not everybody uses it. Sometimes people just say molecules. I say deal with it. It's okay. When I hear people say that you have molecules of salt, it kind of hurts my ears, but that's okay. So, speaking of salt, NaCl, 1 mole of salt equals 6.02 times 10 to the 23rd formula units of NaCl. Now, the mass of that is 58.5 grams. That's what we call the molar mass. We add the mass of sodium, 22.99, plus the mass of chlorine, and that gives me the mass of 1 mole of NaCl. Just want to clear up some terms for you. Molar mass is what I use most of the time. It's from the periodic table. The units are grams per mole. But sometimes people use other phrases. They call this the gram atomic mass if they're talking about just an atom, or the gram molecular mass if they're talking about a molecule, or the gram formula mass. So sometimes these words or these abbreviations can be used in place of molar mass. And I don't want you to get that confused. It's all still the same thing. It's all still that number, that atomic mass from the periodic table. Now, when Avogadro first started talking about moles, he was looking at moles in volume. Now, it turns out that every gas has the same volume. Gases all have different molar masses. You might have heavy gases or light gases, gases that have a lot of atoms attached to them, gases that are just O2, like 2 atoms, but they all occupy the same volume. And that's what Avogadro found, and that's where the mole was discovered. All gases take up 22.4 liters. That's 1 mole of any gas. So if you have 1 mole of carbon dioxide, it takes up 22.4 liters. If you have 1 mole of oxygen gas, it takes up 22.4 liters. So 1 mole of any gas occupies 22.4 liters. And I'm careful to say that that is at standard temperature and pressure, which turns out to be 0 degrees Celsius and 1 atm. Because of course, if we make things hotter or colder, it's going to change the volume. I don't know if you knew this, but if you take this basketball and you put it outside in the winter for a long time, or for even a couple minutes, it's going to deflate. And that's because the temperature changes the volume. And we'll get to this later, but for right now, everything we do is going to be at STP, or standard temperature and pressure. And this is the flow chart that you can use. These are the dimensional analysis problems that we're going to use. 1 mole equals 22.4 liters, 1 mole equals 6.02 times 10 to the 23rd particles, and 1 mole equals the molar mass from the periodic table. As you can see, all roads lead through the mole, which is why the mole is so incredibly important, okay? These are the conversion factors that we're going to be using to solve these problems. Particles is just a word we use for a little tiny thing. It may be atoms, it might be molecules, it might be formula units, it really could be donuts. It doesn't matter. 1 mole equals that many particles. 1 mole at STP has a volume of 22.4 liters, and 1 mole has a mass of the molar mass from the periodic table. Examples. The first one says, what is the mass of 1 mole of calcium sulfate? So the first thing I'm going to need to do is I'm going to need to go to my periodic table and find calcium 40.08. There's calcium. Sulfur 32.07. And then oxygen is 16. So after going to the periodic table, I can add what we call the molar mass of calcium sulfate. So calcium was 40.08 grams, plus sulfur, which is 32.07 grams. Plus, there are 4 oxygens. So that's why I have to have 4 times oxygen has a mass of 16 grams. So those are the numbers that I'm adding together. Make sure when you use your calculator, depending on what calculator you're using, you're putting those in your calculator correctly, right? I am going to start with my oxygen, which was 4 times 16. I get 64 from the oxygen, plus 40.08 plus 32.07, which gives me a molar mass of 136.15 grams. That's how much 1 mole of calcium sulfate will weigh. Now, if I had 2 moles of calcium sulfate, it would weigh double that. As far as the sig figs, there are no, there's no measured quantities in this problem. It just says 1 mole, so I don't really need to worry about sig figs for this one. For the second one, it says, how many moles are there in 67.2 liters of CO2? So let me think about things that I know. I know that every gas, 1 mole of every single gas at STP, and if the problem doesn't say STP, it means it, weighs or has a volume of 22.4 liters. That's my conversion factor. So the question is, well, how many moles then are in 67.2 liters of CO2? Well, I know that every 1 mole has a volume of 22.4 liters. My liters are going to cancel, and I'm going to be left in moles. Putting that into my calculator, it's 67.2 divided by 22.4. Okay, so that gives me an answer of 3. Now, I do need to pay attention to sig figs here, right? Because this is a measured quantity of 67.2 liters, which has 3 sig figs. So my answer should really be 3.00 moles, should be my final answer there. And I always like to put a box around the final answer. Here's one more example. This one gets a little bit tricky. It says, what mass of silver chloride would be obtained from 3.0 times 10 to the 25th molecules? So I've got a couple steps here. First of all, I can see in my problem, it's mentioning mass. And if I think back to my flow chart, mass and molecules are on opposite sides of the flow chart. So you have to go through the mole. So the first thing you're going to do is find the molar mass of silver chloride. So silver is 107.87. Chlorine is over there at 35.45. So first thing I'm doing is finding the molar mass. And the molar mass, again, silver is 107.87 plus chlorine, which is 35.45. This is giving me the molar mass in grams of 1 mole of silver chloride. So 107.87 plus 35.45 equals a molar mass of 143.32. And I know that that means that that's how much 1 mole of silver chloride weighs. And I told you guys this is going to be, the molar mass is something you're going to use over and over again. You are going to use it as almost second nature because this is a conversion factor that I'm now going to use in this problem. So the problem starts like this. I've got 3.0 times 10 to the 25th molecules. Now, be careful with the abbreviation for molecules. There really isn't one because you want to make sure you don't make it look like a mole, because a molecule is not a mole. So I have that many molecules, and I know for every 1 mole, there are 6.02 times 10 to the 23rd molecules. That's how I'm going to cancel out molecules. But I'm not quite done yet because the question wasn't how many moles are there. The question is, how much does it weigh? What is its mass? So again, for every 1 mole, it has a mass of 143.32 grams. That's the conversion factor I just found out. You can see here everything cancels. Molecules is going to cancel. Moles is going to cancel. And I'm going to be left in grams. Now watch how I type this into the calculator. I'm going to take the first number, 3.0. I'm going to use the EE button times 10 to the 25th divided by 6.02 times 10 to the 23rd times 143.32. So that's all going to come out there. And I'm going to get an answer of 7142, which sig figs is 7,100, and that's in grams.